All right. Okay, so we'll get started again. So what I was saying is that some chlorine does dissolve in water. Actually, a decent amount of chlorine can be dissolved in water. This has a very faint yellow color to it, yellow-green color. But you can get this to a very bright yellow-green color, and that indicates there's a lot of chlorine dissolved in the water. And you probably can see the gas. Chlorine's a green gas. You can probably see it degas here off the surface. Cloud up here, and so that's highly concentrated. So chlorine isn't like totally insoluble. You can get a decent amount. If you're bubbling the chlorine gas in water, you end up saturating it. You end up saturating the water with chlorine. So when they're bubbling it, they're going to get a very bright yellow green color here for the solution, which we don't see here. So there's a lot less concentrated. Over here, this is 0.1. Well, actually, I'll talk about this. This tells us how concentrated this is. This number is 0.1, capital M. This is 0.1 moles per liter, moles of potassium iodide in a liter. And so this is what that capital M means. So it's pretty dilute. This potassium iodide, we'd call this a CCS. And this would be clear. It's clear because you could see through it, but it's colored. And so we'd call it a clear, green solution, light green solution, something like that. Okay, what they're going to do is they're going to mix these two together in this test tube. The middle test tube is empty right now. So let's see what happens here. So in goes the chlorine water. So that's the chlorine water first. It's pretty dilute, and so it's the same thing on the left. And then there goes the potassium iodide. If you look at the potassium iodide, it's colorless up here, but once it hits the chlorine, what happened? The chlorine took the electrons. Oops. The chlorine takes the electrons from the iodide to make iodine. Now, iodine's purple. It's a purple solid, but you can dissolve a decent amount of iodine in solution. The more concentrated this is, the more purple. You can see it's pretty concentrated up here, and then it's going to just kind of dilute here. So it's kind of this orange color, which is kind of deceptive. But when it gets concentrated, it's quite purple. Iodine's quite purple here. And so the color is a bit deceptive here. We could see the color much easier if we do it in a different solvent. Let's see. The solvent is water. This is done in hexane. And hexane and iodine here, iodine loves hexane. Iodine doesn't like water as much. And so this is doing it, not using water here. So hexane is clear liquid like this. Let's see what they got here. Oh, no, this is potassium iodide aqueous. I probably should turn on the audio here. How long is this? This is only 1 minute. I'll turn on the audio.
In the halogen-halogen single displacement reaction, we will react an aqueous solution of potassium iodide with an aqueous solution of chlorine. The potassium iodide solution is colorless. When we add the aqueous solution of chlorine, the chlorine displaces the iodine from the potassium iodide, and we get the formation of a reddish-brown solution of iodine.
All right. Maybe let's get rid of this audio. I'll just explain it myself. So this is iodine aqueous, and the color is deceptive. Iodine's purple, but it looks red-orange here. One way we can really see the color of iodine is iodine loves hexane. It loves oils. And so they're going to put a little bit of hexane in here and then shake it up. And then the iodine has a choice. It could stay with water or go with hexane. It goes with hexane. So let's see what happens here. This is called extraction. So in goes the hexane. And so now iodine has a choice. Well, right now it's stuck in the water, but once you shake this up, then it has a choice, because once you shake this up, iodine will either go with hexane or it'll go with the water or both. So they shook it up. They should have shown it shaking it up. They should shake it up more because it'll turn a lot more purple than this. We do this one in lab. We do it with carbon tetrachloride. Iodine loves carbon tetrachloride, and you can concentrate it. And we only use a couple of drops, so we can really concentrate it so it comes out a bright purple color. This one didn't work so well, I think. But anyway, that's enough of that. I think. Let me just see this one here. Maybe they did this better here. Okay. Yeah, that's when it's concentrated. That's the color it looks like. That's iodine concentrated in hexane right here. This gives a nice bright purple color. There's still some residual iodine in the water, which is that red-orange. Okay. Let's move on to the other reaction we're talking about anyway. Just see if the recordings are on. I'll check back on that later. So let's go back to this one. We're talking about copper reacts with silver nitrate solution. So first thing is we have to get the formulas right. This is not copper ion, that's copper metal. You know, otherwise they'd have to say copper 1 or copper 2, you know, or we use the word ion to indicate it. And so we know that it's just Cu, like copper pennies. It's just copper solid. It's not soluble. But nitrate salts are soluble. So if there's water present, this is a solution. So there's water present. It's aqueous. This is a CCS, clear colorless solution. There's no color here. And then we do the reaction. And so this is an A plus BX. This works nicely. It's going to give us our AX plus B. AX would be copper nitrate. Now, the question is, we have a choice. So we're going from A, the element, to A, the cation. Well, there are two cations for copper. There's copper plus 1, and there's copper plus 2. Which one should we use? Well, you don't know. Normally we would do copper 1. It seems to make sense. You know, lose 1 electron is easier, probably than losing 2. But it turns out in nature, copper 2 is more preferred, more stable than copper 1. There's reasons for it. And so most of the copper goes to copper 1. In pennies, we'll see copper 1 oxide first. Eventually, it'll turn to copper 2 oxide. But here, we're going to go for copper 2 because that's what's observed in nature, you know, the predominance of copper 2 and a rarity of copper 1. And so we'll just go with copper 2. If it's copper 2, how many nitrates do we need? Well, each nitrate's a -1, so we'll need 2 nitrates for that. So we're going to form CuNO3, 2. I don't bother worrying about balancing until the very end. And then we'll form silver, the element. Well, silver, the element, is a solid, liquid, or gas. Well, silver is a solid, and it's not soluble. You know, you can't dissolve silver metal in water. And so what about copper 2 nitrate? Will that dissolve in water? And so is copper 2 nitrate soluble? Yeah, well, all nitrates are soluble, so this is going to be aqueous. Yeah. Okay. All right, this is what we call the CE. And then what we do is we look for driving force. So we go to the activity series. You know, what's more stable, copper or silver? You know, so what would you rather have? Let's say copper jewelry or silver jewelry if you want long lasting or longer lasting, you know. Well, copper is much more reactive, you know, it's less stable, it's more prone to oxidation than silver, you know. So quarters retain their luster much longer than pennies do. You know, pennies, you'll see those become oxidized pretty quick. You know, you'll have fresh pennies, but if you have a fresh quarter, yeah, it's got a nice luster, but eventually it will tarnish. Silver will tarnish, but at a much slower rate. And so silver is more stable. It's less active than copper. Copper is more active. And so this is a downhill, you know, copper being more active has higher chemical potential than silver. This is the activity series. And in other words, that copper is a stronger reducing agent than silver. Silver is a weaker reducing agent. So we're going from a stronger reducing agent, copper, to a weaker reducing agent, silver. AKA, we're going from a more active copper, more active being easier to oxidize, to less active silver. And so using the activity series, we say more active to less active here. And we call this the driving force. Now, we want to better understand this reaction in detail. So we look at the ionic equation. When we look at the ionic equation, we got a chunk of copper in there. But when we look at silver nitrate in that beaker, you know, the silver nitrate, which was the CCS, consists of really, let's balance this. Sorry, I forgot to balance it. We need 2 nitrates here. And that's going to give us 2 silvers, which we'll have to change over here. We have silver ions floating around in there. And so this is bookkeeping, 2 silver ions. And we're going to have 2 nitrate ions. You know, each silver has a nitrate. So we got to make sure we keep the books on that. Everything's balanced. We don't lose anything. And copper 2 nitrate is this is strong electrolyte. This is also a strong electrolyte. Soluble salts are strong electrolytes. So that's going to have copper 2 ions and 2 nitrate ions. Here. And then the silver is not a strong electrolyte. You know, and so we leave it alone. We only dissociate the strong electrolytes. Then we look for spectators. Are there any spectators here? It looks like nitrate. Nothing happened to the nitrate. That's a spectator. And so here we have copper solid plus 2 silvers. And the nitrate, nothing happens. We can cancel those out of the net ionic equation. And we're going to end up with copper 2 plus 2 silvers here. Can you guys hear me? Yes, okay, good. If we want to completely analyze this, in completely analyzing this, copper is our reducing agent. It's losing electrons. We're going from copper to copper 2 plus. Silver ions are our oxidizing agent because it's taking electrons here. Now, we're looking at which direction's downhill. Is going forward downhill or is going reverse downhill? So if we were to go reverse, then copper 2 going backwards gains electrons. And so this would be our oxidizing agent. And silver going backwards would lose electrons. This would be our reducing agent. And then we compare the two, you know, copper versus silver, which one's more stable? Silver is more stable, therefore it's weaker. Copper is stronger, it's less stable, more reactive. Which one's a better oxidizer? Well, if this is the case, then that means silver ions have to be a better oxidizer than copper. You know, copper ions. So silver ions are a pretty good oxidizer, as I mentioned before, and they're better than copper 2 ions. And so the driving force, the downhill direction is in the forward direction here. So the driving force is forward, not reverse. Here. And that would be. Well, we can't go reverse because we don't have any copper ions and we don't have any silver metal in this mixture. So we can't go reverse. But this is just hypothetically if we, you know, comparing which way is downhill. Okay. And so the net ionic equation looks like that. Okay. Let me clear the drawings. Okay, that's it for our books, but let me talk some more about single replacement reactions. Okay. So we have our pattern for a single replacement, you know, A plus BX plus yields AX plus B. We have this kind of basic pattern here. And there are going to be, you know, known exceptions to this. One is the halogens. You know, chlorine plus potassium iodide. And so here we use alternate pattern. Or chart method. We can use the chart method for all these, you know, or chart method. Two, mineral acid versus oxidizing acid. So let's look at a mineral acid. Let's say, you know, copper reacted with the silver, but it turns out copper won't react with HCl, hydrochloric acid here. And so HCl is called a mineral acid. What would we form here? It's going to form the A plus BX pattern. So it's going to form copper chloride, but is it going to be copper 1 chloride or copper 2 chloride? It should be copper 2 chloride. Why? Because that's what's observed in nature. Copper 2 is preferred, so we'll need 2 of those. And hydrogen, but hydrogen is diatomic, so it'll be H2. H2 is a gas, it's not soluble. Chlorides are all soluble. Chlorides are all soluble except for silver, lead, and mercury, so this is not one of the exceptions. So this is soluble, so we call it AQ. HCl, it's an acid. And so when I say acids are soluble, it's group 1. Group 1 is H. H is in group 1. All group 1s are soluble, so all acids we're going to take as soluble. And so this is AQ. Now, is there a driving force for this? And so what we need is we need the activity series. So I need to fast forward the activity series here. So what we're going to do is we're going to compare the activity of copper versus hydrogen. Now, what would you, do we really need the chart for this? You know, because the lower the activity, the more stable it is. The higher the activity, the less stable it is. And so what would you rather have? Would you have a pocket full of pennies or a pocket full of hydrogen gas? You know, what do you think would be more stable? You know, if your back pocket was filled with pennies or if your back pocket was filled with hydrogen gas? Based on your experience. Yeah, pennies. So, you know, I don't need the chart for this one. I know that copper is less active and hydrogen is much more active. Hydrogen's easy to burn. Is copper easy to burn? Hydrogen is easy to burn. Is copper? No, copper is not easy to burn. Will copper burn? Will copper burn? Yeah. Copper will burn. I don't know if you've ever seen it burn. Let's see. Let's see the video of copper burning. Go back here. It has to be powdered, you know, and so powdered metals are dangerous. Those powdered metals burn. Powdered copper, combustion, let's just say combustion. Powdered copper, hopefully that gives it to me. I could do this. I might not have it. In fact, it can possibly explode. Let's see if I can get a powdered metal explosion video. let's use aluminum here, or iron. We can do aluminum or iron. Copper is going to burn less intensely than aluminum. Aluminum should burn quite nicely. Let me clear these drawings here. There's aluminum dust, and then they ignite it. Aluminum would be more explosive than copper. You know, iron is going to be less explosive than aluminum. You know, it depends on the strength of the reducing agent. You know, sodium would be very explosive there. And so, yeah, the metals are reducing agents are fuels. We call fuels. You know, they can subject to oxidation. Once I was going to a gas station. One of these cars, the car caught on fire. And the metal was burning. That's a pretty impressive sight. The whole engine just was burning, and there's a pool of molten metal at the bottom, but it was so hot, you know. Okay, let's go. I wanted to show when you buy powdered copper metal, there's a warning, you know, flammability warning and explosion hazard warning on it. You know. I didn't want to delete all that stuff I had written there, but it's all right. So we were talking about, you know, mineral acids. So let's continue. So what's more explosive, do you think? Copper metal? Well, a penny's hard to burn, admittedly. It's very, very hard to burn. It burns very slowly. Or hydrogen gas. Hydrogen gas for sure. So the hydrogen gas is more active. We don't need the activity series. We could just use just basic experience. This is less active. So which direction is downhill? Is the forward direction downhill, or is the reverse direction downhill in this case? So we're going from less active to more active. The reverse direction is downhill. This is the downhill direction. Well, we don't have this. We have this. And so this one wants to go downhill, but we're stuck at the bottom of the hill, and we can't go up the hill. And therefore, what we say is, therefore, NR. NR stands for no reaction. And so what that means is that, you know, the copper shouldn't be attacked by the hydrochloric acid, you know, because we have no driving force for that. And so copper is stable in the presence of hydrochloric acid. And so if we tried to eat up the copper metal with hydrochloric acid, we're going to have no luck. We're going to have no reaction, and this is correct. When we have no reaction, we don't do the IE and we don't do the NIE. That doesn't mean there's no reaction. There's no point in doing that. But, you know, if we were to do the IE, it would look like this. We'd have a chunk of copper in here. You know, that's our copper solid. And then we have H+ ions trying to attack it. You know, chloride is a spectator. So chloride is just hanging back, doing nothing except maintaining charge neutrality. And the H+ is here trying to take electrons. H+ is trying to take the electrons from the copper, but it's not powerful enough. Copper going to hold on to its electrons. H plus is not powerful enough to take the electrons. In fact, all mineral acids, all mineral acids in redox, mineral acids, X is a spectator, HX. H plus is the oxidizer, and X is the spectator. H plus is a decent oxidizer. HCl can't oxidize copper, but it certainly can oxidize magnesium. It would have no problem eating up magnesium. Aluminum too. If aluminum was around, HCl would eat it up. You don't want your aluminum metal to come into contact with HCl because HCl will just eat it up and form aluminum chloride. And so H plus is a good oxidizer. It's this is about a mid-strength oxidizer. This is about a mid-strength oxidizer. It's kind of in the middle. It's not the strongest, it's not the weakest. It's kind of in the middle. So that's why I'm calling it a mid-strength oxidizer. However, when we're dealing with oxidizing acids, we have a different picture come up. When we're dealing with an oxidizing acid, X doesn't want to be a spectator. And so when we're looking at HX, X is no longer a spectator, not a spectator. X turns out to be the oxidizer. And so it turns out that what we have here is a situation where X is going to be minus something. X minus, it could be -1 or -2. X or -3. X is the oxidizer. In other words, X is a better oxidizer than H plus. And so examples of oxidizing acids would be, mineral acid would be like HCl. Acetic acid would be HC2, H3O2, HI, HBr, etc. Examples of oxidizing acids would be like HNO3, HClO4, HClO3, H2SO4, etc. These are oxidizing acids here. Let's take a look at HCl4, for example. When I look at a beaker like this, that's labeled HClO4, here, what's inside there? Well, HClO4 is a strong, first off, it's group 1. Group 1s are soluble in water, so it's aqueous. Next step is it's a strong electrolyte. So strong electrolytes are going to be dissociated into ions, or they're going to be completely ionized in water. That is, we're going to have H plus ions and ClO4 minus ions. ClO4 minus, what's the name of ClO4 minus again? Good, gotcha. That's good. That's correct. And we look at it now. H plus wants electrons, right? What does perchlorate want? Does perchlorate want electrons, or maybe it's happy as is? What do you think? Is perchlorate very happy in its current status? No, perchlorate is kind of unhappy. What makes it so unhappy? Well, let me say, perchlorate's kind of unhappy, and it's unhappy because it would like what? What do you think perchlorate would like? To make it a little happier. Electrons. Good. Kazra, you got it. You're on it. So, but you think, wait a minute. I don't agree with that. This would be the skeptic. I don't agree with that because perchlorate has a negative charge. How could perchlorate want electrons? It already has an extra electrons. So I don't believe you. I don't agree that perchlorate wants electrons because perchlorate's negative and it has, it's got to have an extra electron to create a negative charge because it's the only thing that creates negative charge, electrons. What would you say? This is what you got to think in science is you're always thinking like this. You're always thinking about, what are the holes in my argument? What are some obvious questions? Because you're always going to be challenged. This is one thing. If you don't like to be challenged, and your ideas challenged, or if you don't like to be confronted, then, this is, well, maybe in all fields it's the same thing, but especially in science, because the way science works, you're always going to be confronted. You're always going to be challenged, people are always, and it's like, okay, you get into like these kind of arguments, back and forth arguments. That's just part of science, People are going to be criticizing you all the time, and you just kind of get used to that. And it's good, actually. That's how the scientific method works. So if I claim that there's alien life in Mono Lake, then I'm going to be criticized. Alien, but terrestrial life. I'm going to be criticized, but you got to be willing to deal with that. And so somebody might argue, yeah, I don't believe perchlorate wants another electron. It already has an electron. What are you going to get? Perchlorate 2-. So it's not necessarily the perchlorate that wants electrons. What in perchlorate wants electrons? So when we analyze perchlorate, we have chlorine plus how many oxygens? 1, 2, 3, 4. So that negative charge actually doesn't belong to chlorine. That negative charge actually belongs to the oxygen. And the oxygens are happy, right? Oxygen likes to be -2. Those are all happy as is. And so this is going to give us -8. This is supposed to be an 8, -8. That negative charge is a result of an imbalance here. And what does that make chlorine? What's the positive charge? What's the oxidation state on chlorine? That's the normal charge range, Kazra, is from -1 to +7. In this specific ion, what is the charge on chlorine in this specific ion? Have you guys been reviewing your notes? I already gave you this the other day. It's +7, yeah, or 7+. I'm going to call it +7. +7. So that's maxed out. It's lost all of them that it can. And so perchlorate wants electrons because of the chlorine is unhappy. The oxygens are very happy. And that negative charge results from oxygens being happy. The chlorine's unhappy. So even though perchlorate is negative, it wants electrons here. It's going to rearrange things. The atoms are going to rearrange and everything else. But it turns out that when we compare this, both of these are oxidizers. When we compare HCl, H is an oxidizer, but chloride is not an oxidizer. Chloride's a reducer. Chloride is Cl-, it's happy. But over here, this is not. And so we have two oxidizers here. And it turns out when we compare these two, perchlorate is a much more powerful oxidizer than H+. Perchlorate's at the top, where H+ is mid-range. H+ is a mid-range oxidizer, but perchlorate is a powerful oxidizer. So if you're the director and you say, okay, H+, you're going to be the oxidizer, what do you think perchlorate's going to do? Perchlorate's not going to listen. Yes, okay, you're the director, you say H+ is going to be the oxidizer because then it fits our nice little pattern, and our nice little pattern is A plus BX. And you want B to be the oxidizer, but X completely refuses because X is perchlorate. X is not going to listen at all. And so if a metal comes in here like copper, forget it. H+ is going to lose. Perchlorate's going to attack. perchlorate, the X attacks, and we get reaction. So oxidizing acids, X is a more powerful oxidizer. X is the oxidizer. X is more powerful than H plus. Well, what are the products? The products depend on what oxidizing acid. We have to memorize a pattern for HNO3. We'd have to memorize a pattern for HClO4, a pattern for HClO3. We'd have to memorize a pattern for each of these. Do you want to memorize that many patterns? It's too many patterns to memorize. And so once we get to oxidizing acids, I give up. I don't want to memorize any more patterns. You know, 2 patterns is about my max. So you have a choice. One, you never deal with oxidizing acids, like nitric acid, perchloric acid, chloric acid, sulfuric acid. One, you never deal with oxidizing acids, so that's not part of my little play area. But you can only go so far. You can only go to kindergarten level. If you want to go advanced, then you have to deal with everything, you know. Since we have to deal with everything, then we got to use the chart method. You know, there's too many patterns. And so for oxidizing acids, we must use the chart method. Must use the chart method. Otherwise, there are too many individual patterns to memorize. Must use the chart method. All right, the next failure of the single replacement method is this. And so we'd have to memorize another pattern for this one. And so another problem. Okay. This one is, what is a mineral acid? What is an oxidizing acid? Mineral acids, the X is not a powerful oxidizer. So here, X is chloride. Chloride's a reducer. You know, chloride doesn't want electrons. It's already happy. Acetate is a reducer. Doesn't want. Iodide is a reducer. This, I don't remember what I wrote here, but it's probably bromide. Bromide is a reducer, you know. And so we're looking at X. And so for mineral acids, X is a spectator. H plus is the oxidizer. For oxidizing, this is redox properties of acids, redox props of acids. Oxidizing acids are a different story. X is not a spectator, not a spectator. X turns out to be a more powerful oxidizer than H plus. H plus is a decent oxidizer. H plus is a mid-strength, this probably can't read that. It's a mid-strength oxidizer. H plus is a decent oxidizer, but H plus is only mid-strength. Perchlorate is a top-strength oxidizer. It's a powerful, powerful oxidizer. And so if there's a competition between H plus and perchlorate, perchlorate is going to win. But that's not what we have in our pattern. In our pattern, X is supposed to be a spectator. Our pattern goes A plus BX yields AX plus B. X is not supposed to react. In our single replacement pattern, X is not supposed to react. But if you let things react naturally, X will react here. And so for oxidizing acids, X is the oxidizer, not H plus. Because X turns out to be more powerful. Nitrate turns out to be more powerful than H plus. Did you guys see the China explosions? let me show you the China explosions, and then you can get an idea of nitrate. Nitrate is actually, it's not a top rank. Perchlorate's more, but nitrate is a high level, high strength oxidizer. Now let's look at the, gosh, they keep, I had the links, but the links keep changing around in YouTube, fortunately. So nitric acid, nitrate is a great oxidizer. So when I look at hydrochloric acid and compare it with nitric acid, hydrochloric acid is a decent oxidizer, mid, but nitric acid is a powerful oxidizer. It's because of the nitrate. I'm gonna have to erase this again. Let me go to, this was our aluminum dust explosion. Go to the explosions. Oh, this one's a good one. This is the phone video of this one. It's pretty good. Hopefully this one's not all edited. That's not the one I wanted, sorry. I wanted the one at the hotel. Let me see if this was the one that they're even closer. Maybe they might have it here. There's one that's even closer. Find it. That's not the one. That's it. Hopefully I don't have to subscribe to the Times. I think this is it.
What the? I think that might be a gas station or something. No, it's a gas. Whoa! Oh! What the? We're dangerous. Oh my God. Oh dear. Are you filming? Yes, I'm filming. Wow. Wow. I think we are dead. Let's go. Let's go down. Let's go. Let's go. Take the stairs. Come on.
Yeah, so that was a, redox reactions can be very violent. And so you have to be very careful with redox reactions. That is so crazy. But that turned out to be ammonium nitrate. And let's see. So there's warehouses filled with ammonium nitrate. Well, ammonium nitrate is okay as long as it doesn't get too hot. If it gets too hot, that's a problem. So let's compare the two nitrogens here. This is with oxidation states. So first we'll look at ammonium. Ammonium has a positive charge. So you might think, oh, positive charge, it's electron poor. Oxidizers are electron poor, so you might be you might be tempted to call ammonium an oxidizer because it's got a positive charge and probably wants electrons. But ammonium is not an oxidizer. This is a good reducer. You can burn ammonium ions. You know, ammonium will burn. It's a good reducer. And that is, the H's are all H plus in this case. And so we have 4 of them. And that makes nitrogen here, it's got to be a 3 minus. 3 minus plus 4 is going to give us plus 1. And so this nitrogen we call electron rich. Electron rich. Reducers are electron rich. And so this is why it's a good reducer. It's electron rich here. Metals are electron rich. Metals are good reducers. Nitrate is a good oxidizer. Good oxidizer. And so the problem with ammonium nitrate is you have a good reducer and a good oxidizer right next to each other in a lattice. And so we have ammonium ions and then nitrate ions and then ammonium ions. They're going to be packed together in a crystal lattice in the solid, you know. And so we got a lattice of ions here. Nitrates, ammonium. And they're okay if they stay apart. But if this starts to get hot, and when it gets hot, you get more kinetic energy. And if we get more kinetic energy, we get bigger vibrations, which can cause these to collide into one another. You know, if you start, you know, it's okay if everybody stands still. If everybody's standing still, they aren't going to react with each other. But all of a sudden, if everybody's running around, you know, as much as they can't run around too much because there's no translation, but they can vibrate back and forth into one each other. And if they back and forth, vibrating one into the other, eventually they can react. And so ammonium nitrate is what we call metastable. Metastable means, okay, it's okay right now as long as it's cold, but if it gets hot, watch out. It's going to be quite unstable. It's going to be quite unstable. We talked nitrate. Nitrate, it has 3 oxygens. Oxygen likes to be -2. That means nitrogen is what? If oxygen's -2, then that means nitrogen is what? +5. Or 5 plus. What does nitrogen vary from? Nitrogen varies from -3 to +5. We have one nitrogen at one end of the spectrum, and we have the other nitrogen at the other end. So these 2 nitrogens go, okay, that nitrogen's very rich, and this nitrogen is very poor. What happens when they come into contact with one another? You know, they're 2 nitrogens, they're the same. And just one is very rich, the other is very poor. What's going to happen is you're going to get some exchange of electrons. The very poor one is going to take the electrons from the very rich one. So this is electron poor. Electron poor species are oxidized. A lot of people don't think it's electron poor because they see this negative charge. Well, that negative charge is a result of the oxygens, and the oxygens are happy like this, but the nitrogen's not happy. Yeah. And so that's electron poor. And so ammonium nitrate is not a happy compound, you know, because of this distribution of electrons between the 2 nitrogens, you know, as we see it here. And so that resulted in, I guess it got hot, or maybe there was a spark or something, and that created the problem. That's not the only spectacular explosion with ammonium nitrate. Oklahoma City bombing, there's a picture in your book of the Oklahoma City bombing. I mean, that almost leveled that huge building, the federal building in Oklahoma City. It killed lots of people, that particular explosion. You know, that was a terrorist act there. But there have been accidents that have occurred. You know what the worst industrial accident in the US is? The worst industrial accident that killed more than 500 people, I think. It was an accident in Texas. It was an accident in Texas City. Actually, let me show that to you. Hopefully I can find the right video, because there's so many videos I need to find. think this might be it. Let's see. Hopefully that might not be it. Maybe this is it. This is it.
Some memory.
This is not the one, sorry. It'll take me a minute to find it.
You can't always plan when you'll need a gun. Rational gun owners carry not because it's a weapon, but because...
Skip that out.
We are approaching the 70th anniversary of the Texas City disaster. The industrial accident killed hundreds of people and left thousands injured. This morning, a memorial service was held to honor the firefighters who lost their lives. Channel 2's Jake Reiner was there. He joins us now from Texas City. Jake?
That's not the one either. I'll have to find it. I'll show you the Texas City one later. Let's go back to this. And so Texas City is another ammonium nitrate, which was just a pretty amazing explosion. But unfortunately, a huge number of people were killed in that one. Okay, let's go back to talking about this. So with oxidizing acids, we would have to memorize a pattern for each oxidizing acid. And the way we recognize the oxidizing acids is by looking at the anion. You know, when we compare, we want electron poor anions. So what do all oxidizing acids have in common? They all have electron poor anions. And when we compare, let's say a mineral acid, let's go here, like HCl, you know, we got H plus and Cl minus. Well, Cl minus is not electron poor. We got acetic acid, which would be H plus, which would be electron poor, and then we'd have acetate here. Acetate, well, let's take a look at acetate. And so we have two oxygen, well, the hydrogens get assigned first. So we have 3 hydrogens. Those get assigned first at +1. And then the oxygens get assigned next at -2. So we give everybody what they like. But that leaves carbon. We have 2 carbons. So what is each carbon in acetate? Well, each carbon, well, this whole thing has to add up to -1. So we got +3, -4 is -1. So each carbon must be 0. That's the average. That's the average. And so the oxidation states are going to be 0 here. This is the average. The way we do it here, pretty soon we're going to do this structurally, where we'll see what the oxidation state on each carbon is on this, which would be a more accurate description. But the situation about carbon is carbon varies from -4 to +4. And so 0 is right in the middle. So what that means is 0, it means it could lose electrons, that is, lose electrons going to more positive, or can gain electrons going more negative. And so in this case, acetate can lose more electrons. Well, if acetate can lose more electrons, then can you burn acetic acid? Will acetic acid burn? And the answer is yes, acetic acid, you can burn it, you know. Can you burn it? Well, HCl is harder to burn because chloride's harder to burn, you know. But acetic acid should be more easy to burn than that. Okay. Whereas when we look at an oxidizing acid, like for example, HNO3, then H plus, and then nitrate. And well, we know nitrate, when we look at the oxidation states, nitrogen's at +5. You know, this is it. Now nitrate, HNO3 is okay because nitrates can't take electrons from H plus. And so HNO3 is not what we call metastable. You know, this is stable, you know, as long as, you know, there's nothing we're reacting with. However, something like ammonium nitrate is what we call metastable. This is a ticking time bomb. This is a ticking time bomb because nitrate can't oxidize H plus because there are no electrons to take. You know, Hydrogen lost all its electrons. However, nitrate can oxidize ammonium. So this is why this is a ticking time bomb. This is a ticking time bomb because nitrate can just go ahead and try to oxidize that. But as long as everybody stays still, and as long as everybody stays in their position, then it's metastable. It's stable, it's not going to explode. But once the ions start moving about, you know, kinetic energy goes up, then things aren't so stable, and things can potentially explode. It's like O2, you know, as long as we don't fill this room up with methane gas, then I don't have to worry about an explosion. You know, I'm just breathing air, and so I'm fine. I can breathe in O2 in air. But if I start filling this room up with methane, then a mixture of methane and oxygen is metastable. This is an explosion waiting to happen, you know. And methane gas explosions happen every year, killing lots of people. I think about 100 people per year, they say, or something like that. I don't know what the number is. It's surprisingly high. You wouldn't think it'd be so high, but it's surprisingly high. Okay, let's, and so this is a difference, you know, we look at the anion here. And so mineral acid has an anion that's not an oxidizer. An oxidizing acid has an anion that is an oxidizer. And some of the other ones were chlorate, you know. Chlorate, well, this, rather than being +7, this is +6. It's still very high, you know. Chlorous acid or chlorite, you know, is an oxidizing acid. Hypochlorous acid is also an oxidizing acid, you know. This would be +3. This would be +1. And so we look at the anion, and we look, you know, hypochlorite's a good bleaching agent. It's an oxidizer. It's not as powerful as perchlorate, you know, so it's not going to be as explosive, but, you know, it's still explosive, and it's still, I don't know how many people are killed by this reaction per year. The people who pour bleach and ammonia in the sink never mix bleach with ammonia. Never mix bleach with ammonia. It has potential to cause a little mini explosion. And so what happens at the home is people pour bleach down the sink, and then they start pouring ammonia cleaner down the sink. The problem with pouring ammonia cleaner down the sink is that ammonia is electron rich. Ammonia can burn. Nitrogen is -3, just like in ammonium, nitrogen is -3, it's maxed out. Nitrogen varies from -3 to +5, you know, and the hydrogens are +1. Well, you put that in, you mix it with this, you know, chlorine's +1, although this is, you know, written differently. Oxygen's -2, oxygen gets assigned first, no matter what order. And so bleach is often written NaOCl or NaClO. ClO is our convention, but on the ingredients, it would probably list it as NaOCl. As people might think this is salt, sodium chloride. But anyway, so we don't mix ammonia with bleach because we might have a little mini explosion. Ammonia is electron rich, bleach is electron poor, and redox reactions like this can result in explosions. Okay. The next problem with single replacement is it ignores the solvent. The solvent is water in this case. Solvent is what's all dissolved in. It's dissolved in water, so that's what we call the solvent. And so an example of that would be, let's take sodium metal and potassium chloride. If we take sodium metal and potassium chloride, this will be aqueous. Then what do we predict? We predict sodium chloride and potassium metal. And then we look at the activity series. Well, potassium metal is higher in the activity series than sodium. You know, this would be activity series here. So potassium is less stable than sodium. So what this is saying, this is more active. This is less active. And so what we do is we predict no reaction. So because this is going uphill, you know, less active to more active. We're going less active to more active. This is uphill. We want to go downhill. And so what we expect is the reverse reaction is favored. Downhill directions reverse. And so potassium to sodium is downhill. Potassium to sodium is downhill. Unfortunately, we don't have potassium, we have sodium. So we're going here uphill. So we say no reaction in the uphill direction here. Reaction would be in the downhill, the reverse. So no reaction in the uphill direction. This is very dangerous because if you mix sodium with KCl-AQ, you're going to get an explosion. You know, why? Because KCl-AQ consists mostly of water. And what happens when you mix sodium with water? Sodium metal with water, not sodium ion. And so over here, if we inventory this is called an inventory. We got potassium ions. This is strong electrolytes. Soluble salts are strong electrolytes. We got chloride ions, but we also have water. And so this is the wrong reaction. The reaction is actually between sodium and water, not potassium chloride. The whole thing is a spectator. KCl is a spectator. So how do you know to worry about water reacting? Water is always present in these. If water is always present, then how do we know when to worry about water and when not to worry about water? It's what we're dealing with. If we're dealing with a powerful reducer, then we always got to worry about water. You know, potassium metal, sodium metal, the alkali metals. If we were dealing with the alkali metals are such powerful reducers. Water is a very weak oxidizer. We got to worry about a potentially violent reaction occurring there. And so there is actually a reaction here. There are two ways of doing the reaction here. There's a reaction between sodium and water. And so one way of doing this in the single replacement form is called water HOH. And so this would be A plus BX. So if we call it HOH, then what's going to happen is we're going to form sodium hydroxide and hydrogen gas. And we'll need two HOHs. We'll form two sodium hydroxides. We'll need two sodiums to get the hydrogen gas. Sodium hydroxide, all sodium salts are soluble like this. HOH is a pure liquid. It's just water. Or, so this is another pattern we remember, or use the chart method. But we've got to remember two things. One, you know, sodium versus water. Water is more reactive. Sodium, actually not sodium, KCl versus water. Water is more reactive in this case than potassium ions, or use chart method. And so if we stick with single replacement, we got to memorize a lot of patterns and memorize a lot of exceptions, you know. So single replacement, the pros, it's easy if it works. It's a simple pattern. Is it break time? What time is it now? Yeah, it's a break time. So, okay. Let's go on break here for 15 minutes. So we'll start again at 2:12. So, right? Yeah, around 2:12, 2:13, something like that. 2:15, no later than 2:15. Okay. Well, maybe we'll just keep it simple. Let's just start at 2:15. Okay. And so we're going to go on break. I'm going to break up the videos into shorter segments. That way, hopefully they'll process faster. I think that my videos are too long, so they're taking a long time to process. So I'm going to stop the recording here.